So we've been talking about linear functions quite a bit already, especially with these ideas of rate of change and kind of our graphs. But let's get into actual linear functions and putting together our linear functions. So a linear equation is our y equals mx plus b, and m is our slope, b is our intercept. Really what we're going to change here is just moving to function notation. So instead of using y, using f of x, but we'll still use that notation m times x plus b. Or, just so you know, it can appear with the slope and intercept part switched. So it could look like f of x equals b plus m times x. And just sometimes I kind of switch between the two, but sometimes it can be nice to have this form with the b plus mx, because often it can be easier to find the y-intercept, because they'll often describe it as an initial value or something that you're starting with, and then they'll describe some rate of change. But really both forms, they're the same exact thing. Basically, slope has to be multiplying your variable. B is just a constant that's separated from your variable. So b represents our y-intercept. It can also be described as an initial value. So it's our value when x is equal to 0. So when x equals 0, this is the output. And then m is our rate of change, and since this is linear that we're dealing with, it's a constant rate of change. So the rate of change stays the same across the graph. Now in terms of word problems, the slope is often given as a rate. So usually it's like miles per hour, dollars per second. Usually you'll see the word per in there to represent this rate of change that's occurring. Something that it could be like dollars each hour or something. So each is another word that can come up that represents a rate of change. All right, so let's look at some different ways of just finding slope. So we're going to look at a table, a graph, and a word problem. So from a table, so here we have these t values of -9, -6, -3, 0, 3, 6, 9, and then f of t has these different outputs, 14, 10, 6, 2, -2, -6, -10. All right, so what we want to do is see how is t changing? So what's the change in t related to the change in f of t? Because for our slope, so for our rate of change here, we want to evaluate the change in output over the change in input. So with the table, what we could do is kind of read from the top to the bottom and see how is t changing. So like -9 to -6, that is a +3 increase. So that increases by 3. And then notice that's actually the same for all of these. And that's a good thing to note, because if the change in t is different, we would need to take that into account. But for this case, it's always +3. Now, if we do the same thing, but with looking at the change in our outputs, so let's see, we went from 14 to 10, so that was a decrease. So we went down 4 units. 10 to 6, we went down 4 units. 6 to 2, down 4 units. And the fact that we're getting the same value each time is perfect. That's the idea of a linear function. If how t is changing is the same across the table, then how y changes should be the same across the table too, because with linear functions, it should be a constant rate of change. So for the slope here, change in f of t, what we're seeing is this change of -4 over this change in t, which we're seeing is a +3. So our slope is a -4/3 coming from this table here. So that's how you can visualize it with just given a table of x values and y values. All right, with a graph, all we need are 2 coordinates. Because really we could have done that with a table, just focusing on 2 coordinates. But as you see, I went kind of across this whole table, but that was just to emphasize this idea of a constant rate of change, like it's always -4/3 no matter where we are. Here, with a graph, what we can do is see that it's a line, like it's a straight line, and that rate of change is staying the same. So let's grab 2 coordinates. Basically, you want to grab ones that are clearly defined. It's really nice if the intercepts are clearly defined. So we have this coordinate 0, +5. We also have this coordinate 4, 0. So with that, let's go with the calculation, and then I'll show you with visually how we're seeing that as well. So in terms of the calculation, we want the difference in the y coordinates. So with this, we're looking at f of 4 minus f of 0 over 4 minus 0, because the 2 x coordinates we're looking at are at 0 and 4. So f of 4 is that output of 0 minus f of 0, which is a +5, over 4 minus 0, which is just 4. So we're getting -5/4. Okay, the way we could have done this just by reading the graph, it's just an alternative way, is making a map from one coordinate to the other. So we want to talk about change in y over change in x. For the change in y, we're looking at how does our graph move up and down. So I'm going to start off to the left-hand side here. So if I'm at 0, 5, to get to my second coordinate, I would need to move down 5 units. So because we're moving down, that's a negative value. If we were moving up, it would be positive. So this is giving me a change in y, which is down 5 units, so a -5. And then for x, this is how we move horizontally left and right. And if I'm now at this 0, 0, I need to move to the right 4 units. So for change in x, moving to the right is positive, to the left is negative. So moving to the right 4 spots is a +4. So in terms of how y had to change, since we had to go down 5 units, that's a -5 over, and we had to move to the right 4 units, which is a +4. So the slope gives us kind of a map to follow in terms of direction of like how the numerator is telling me down 5, denominator is telling me right 4. All right, and just a quick review of our fractions. It doesn't matter how I write this. You can have -5 over +4. That's the same as having +5 over -4, which is just the same as having negative out front, 5 over 4. Those are all the same thing. Okay, let's look at a word problem and how to get slope out of this. So we have in 2003, a town's population was 1,431. By 2007, the population had grown to 2,134, and we're going to assume the change is linear. So that means slope is staying the same. So what we need to do is make our coordinates. We can also define some variables here. So we have time occurring here, and it doesn't matter how we choose to work with time, but we need to be consistent. So what we can do if we didn't want to work with these large values like 2003 and 2007, something we could do is define t as the number of years after 2000. So what that'll do to my coordinates, so if I'm talking about this 2003 when the population was 1,431, that would give me the coordinate 3, 1,431. It's just giving me x values that are easier to work with. And then 2007 would be year 7, and the population was 2,134. So it's just giving me some easier coordinates to work with. So if I want the slope, we're taking the difference in y values, so 2,134 minus 1,431 over 7 minus 3. And with that, let's just hop over to calculator. So we're going to have a fraction with 2134 minus 1431 over 7 minus 3, which is 4. So 175.75. And in terms of slope, this is giving us a rate, like we have context here, so let's talk about this. We could say population, let's even go with the population. The population of this town is, our slope is positive, so it's increasing. And the rate is, so in our numerator, we're talking about our population, which is the number of people. And in the denominator, we're talking about time, which is in years. So this is the number of people per year. So it's increasing by 175.75. If I wanted to round that to a whole number, we could. People per year. All right, just 2 more examples here, talking about our linear functions and applying them to word problems. So, to start producing a new model of custom wheels, a company will have to purchase $30,000 in equipment. I'm just going to highlight that $30,000. That right there is a fixed cost. They have this purchase they need to make. They don't need to make it over and over again. They just need this new equipment. So that right there is a fixed cost of $30,000. Each wheel made costs them $40 in supplies and labor. So this is a cost for each wheel. This is that variable cost. So if this terminology is new to you, make sure you go back and watch that video about marginal costs and total costs. That's where I defined these. So we have this cost per unit and this fixed cost. So we want to write a formula for total cost producing Q wheels. So we basically want to find this T of Q, treating it as linear, and we know it's linear because that variable cost is staying the same. So what will be their total cost in the first year if they expect to sell 240 wheels? Okay, so this total cost function, again, we're taking fixed cost plus variable cost times our quantity. So for us, our fixed cost is $30,000 plus our variable cost of $40 times Q. So there's our function that we're working with. And we want to find what will be their total cost in the first year if they expect to sell 240 wheels. So now we want to find this total cost of 240. So we'll take 30,000 plus 40 times 240. And just plugging that into a calculator, what have you, that should be 39,600. So the total cost in the first year is $39,600 for 240 wheels. That in the first year is important because they probably don't need to purchase new equipment every single year. So that's where this 30,000 is coming in. If they were doing calculations for the second year, like that cost would have been taken care of in that first year. All right, this last one here. So working as an insurance salesman, Maria earns a base salary and a commission on each new policy. So base salary is going to be the idea of a fixed cost for the company, and then commission, so on each new policy, that commission is a variable cost. So Maria's weekly income, the variable I, depends on the number of new policies, N, that she sells during the week. So we're getting some variables here, income and number of policies. Last week, she sold 3 new policies and earned $760 for the week. The week before, she sold 5 new policies and earned $920. Find an equation I of n and interpret the meaning of the components of the equation. All right, so we're given 2 scenarios here. With 3 policies, she made $760. With 5 policies, she made $920. So with 2 coordinates, we can find our slope by taking the difference in the outputs. So minus 760 over 5 minus 3. And plugging that into a calculator, we should get 80 out. Now this gets us started with our formula or our equation for I of n, because now we know our slope. So we know we have 80 times n. What we still don't know is what is our y-intercept. So I'm just going to go plus b. Now to solve for our y-intercept, what we can do is take one of our coordinates and plug it in. And it doesn't matter which one you use, either is fine. So I'm going to go ahead and plug in 760. So we have an income of 760 equals 80 times our n value of 3, and then plus our unknown b. And then we just solve. So 80 times 3 is 240. Subtract 240 from both sides, and that should be 520. So now we have our slope and our intercept. So our last piece is to put our function together. We have a slope of 80 times n plus our y-intercept of 520. Now, as they described above, there's this base salary, so that's our fixed cost. So that's what this 520 is relating to. So that's the base salary for the week. And then the commission, that variable cost, is coming from our slope, which is 80. So in terms of interpreting the meaning of the components, we could say Maria earns a base salary of $520 per week, or let's just put this all in the terms of a single week. Base salary of $520 and a commission of $80 per policy each week. Okay, so this is the idea of getting the equation from 2 coordinates, find that slope first, then plug in one of the coordinates to find the intercept. And then once we have that together, we can tie it to this idea of fixed cost and variable cost. And yeah, just some extra word problems and this idea of slope.